Thank you. Thank you for the opportunity to speak here. I really appreciate it. Thank you for organizing a great conference. I mean, it was perfect until now. Yeah, that's really amazing. So I want to tell you about 3 different applications that seem quite different on the face of it, but of course, what's under the hood is the same. Like it's the same kind of modeling and inference underneath. Here's the first application. The green patients are patients in a current single-arm treatment-only study, and we do the usual game. We want to use readily available external data. We want to use real-world data to construct a synthetic fake control cohort. So down here are the black patients. Those are patients from external data. To use them for a control cohort, we have to make sure that the 2 populations are comparable, lest you get, of course, very biased inference. On the horizontal axis, we have like important baseline covariates. In that particular application in glioblastoma, there are some 10 important baseline covariates that everyone agrees upon. And then what we simply do is we consider a partition of the green patients. We consider a partition of the black patients. And then, for example, here, when you look at stratum 2, you can already see the black patients, they're obviously overrepresented in stratum 2. Just fill it out and remove one of the black patients in stratum 2. In stratum 1, what you might do is maybe duplicate 2 of the black patients. That way you can make the 2 populations comparable. Simple trick, right? For the whole narrative to work, it's important that the 2 partitions need to be aligned, right? Otherwise, I couldn't talk to them. So what we do is we'll set up 2 aligned random partitions for green guys and black guys. We'll average, which marginalize with respect to the partition, but importantly, for a given partition, we thin out on one or the other side. We will not literally thin out, what we simply do is we do some relating to make them comparable. To set up the 2 aligned partitions, we'll of course set up the obvious BNP model, just a special case of multivariate species sampling. The second application, totally different application. In this case, our experimental units, each of the dots is 1 cell. These are immune cells. The 2 plots, one is for early onset colorectal cancer. The other one comes from samples from late onset colorectal cancer. And what we are plotting here are gene expression features for immune cells. We want to cluster the gene expression features of immune cells with the usual fiction. You assume that the clusters correspond to homogeneous cell subpopulations that are different cell subtypes. And we want to find immune cell subtypes that are particularly characteristic of early versus late onset. In this cartoon, you could immediately say the red subtype is very specific for early onset CRC. The background is there's an increasing prevalence of early onset CRC that we didn't used to see before, and it's still not properly understood how early onset and late onset differ. We'll again, of course, proceed methodologically exactly the same way. We'll set up a random cluster arrangement means a partition of gene expression features for those immune cells. We'll do it for early onset, we'll do it for late onset, and then we stare at it and we can see which classes are specific for one or the other condition. Again, for that narrative to make sense, you need aligned random partitions, which I create by way of setting up common atoms texture models. In the third example, again, we have 2 kinds of cells. We have tumor cells and we have immune cells. And in plain English, the question is, our collaborators want to find out if there's maybe some tumor cell subpopulations. They always use the slightly poetic language. They want to find tumor cell subpopulations that recruit certain immune cell subpopulations, as if they were talking to each other. So in blue, it's a little hard to see, but the blue clusters, the blue dots, those are tumor cells. and the little potatoes around the blue dots, those characterize tumor cell clusters. The yellow, orange, and red dots, those are immune cells. And again, by way of clustering, we try to create inference about immune cell subtypes with the fiction that clusters correspond to subtypes. And then we are going to stare at these clusters. If some of the red clusters seem spatially correlated to some of the blue clusters, then we're going to send it to our collaborators as that blue cluster recruits these yellow and red subtypes of immune cells. For that narrative to be meaningful, we're going to set up a random partition of the blue tumor cells, a random partition of the red immune cells, and we set up the two random partitions in such a way that the red clusters could be spatially correlated with some of the blue clusters. And again, I'll do it by setting up two mixture models with appropriate structure in the trial probability model. So all that's coming up is I'll talk you through these three examples, and if Michele lets me, I have the fourth one too. Most of you can probably impute already what's going to happen, right? If you care, there's verbatim copies of the slides on this anonymous FTP site. And let's get started. So again, there were these three applications on the title slide. I want to point out, although these three applications, like I just tried to convince you that these three applications are methodologically exactly the same problem, or at least very similar problems. But the inference target is quite different. In the first case, with the real world data, where we have the green patients and the red patients, we want to find the differences so that we can remove them. We want to remove the differences. Because that's what will allow us to think of it as a fake randomized clinical trial. In the second case, we want to find the differences, we want to find the immune cell subpopulations that are characteristic of one or the other condition, and we want to focus on them. We don't want to remove them, we want to focus on them, we want to highlight them. In the third case, again, it's a little different. In the first two cases, we wanted to have literally matching clusters. Like the first two cases, aligned meant actually matching shared clusters. In the third case, aligned means just spatially correlated. In particular, we only want to have correlation of the spatial subvector. We also observe gene expression features. There's no reason why a tumor cell, gene expression should be correlated to immune cell gene expression. Those are two totally different cell types. So as usual, I'll set up inference about random partitions that we have written down a mixture model. So you can see here xi. So in the first application, xi would be the baseline covariance for patient I. I assume that those baseline covariance come from a mixture model. And below that, I have three more equivalent ways of writing exactly the same mixture model by way of introducing notation. Yeah? The upcoming discussion will use our four notations depending on how it's convenient. So you can alternatively write the mixture model by introducing this red latent indicator. That latent indicator links patient I with cluster J. And if you interpret the red indicator as cluster -G indicator, that explicitly represents the random partition. Alternatively, I can write the same thing as an integral of the kernel with respect to a mixing measure G, where that G becomes now a discrete mixing measure with atoms at the cluster centers theta G tilde. And again, it's of course saying exactly the same thing. And again, equivalently, I could write that mixture model in line 3. I could write it with a latent variable, with the latent red variable theta I. And again, it's saying the same thing. If you look carefully, like many times in life, an important thing to see is what you do not see. You see that spurious gap down here before the I index. This is simply because, remember, on the title slide, I had not only one random partition, but I also had two random partitions. There will be an additional index for the two conditions. So mixture models are an awfully convenient way of introducing inference about random partitions. And as we already heard repeatedly in this conference, it's not only a convenient way of talking about random partitions, it's the only correct way if you want to make a random partition to comply with certain symmetry assumptions. Mr. Kingman, 78. Writing the mixture model is the integral of the kernel with respect to the random mixing measure G. Means if you want to complete the probability model to a full Bayesian inference model, we need a prior probability model for the mixing measure G. At this moment, we are at non-parametric Bayesian inference because now we need a prior probability model for the random measure G. As you all know better than me, that has a long history, starting right here in UCLA with Tom Ferguson. You see the audience? It's a possibility. It's a non-zero possibility, right? Many others, but it's not what I want to talk about today because you guys know it much better than me. Today I want to talk about not only one unknown mixing measure, but we want to talk about two unknown mixing measures. So we want to talk about G1 and G2. In that cartoon of my two discrete mixing measures, G1 and G2, can you see in particular they share the same locations? I need that to introduce the desired alignment of the random partitions. Using shared locations is exactly the trick that gives you alignment partitions. But the weights can differ. For example, in the application to the comparative immune profiling for early versus late onset CRC, that would mean the green cell subtype would be specific to late onset CRC. One more footnote to that. It would be biologically very implausible that some cell subtype would be exclusive to one or the other condition. We don't expect it to be totally missing in the other condition. It might just be characteristic and more prevalent in one or the other. So at this moment, I have exactly the same as on the previous slide, just with the additional index C for the two conditions. So throughout in all four applications, we'll work with random partitions, or sorry, mixture models indexed with the additional index C for the condition. I'll tell the story with two conditions, obviously the same works with one. Now, of course, also setting up prior probability models for a set of random probability measures is also a well-known inference problem. We do it by setting up these two random distributions, G1 and G2, with shared atoms to achieve the alignment. And all what will be different, the weights will be different. In the second application, we'll allow some of the weights to be identical, those are the shared immune cell subtypes, and some to be different, those are the characteristic ones. Of course, setting up prior probability models for families of random distributions is not exactly a new problem either. There is like the DDP and its cousins and its brothers and its uncles and God knows what that we have heard a lot about already today in this conference. I want to convince you in the upcoming discussion, I want to convince you that in those applications, we are looking for a bit more structure than what we usually have in these models. And then set up these maybe trivial models to achieve exactly that. Yeah. So that's what's coming up. I'm just talking off through the three applications until my time is up. So this is the first example on the title slide. Using real-world data to create a synthetic control cohort for a single-arm trial. That's a very popular theme. Yeah? This afternoon in the Bayesian biostat meeting, we'll probably hear more about the same thing. Yeah? This is joint work with Noel Chandra, who is here at the conference from UT Dallas. Noel, he's still sleeping this morning. Very high. Abra Sarkar, my colleague from UT Austin, Ding Yuan in MD Anderson, and from the group in UCSF. So this is now the data for the current single-arm treatment-only study. In the vertical axis is some 40-something patients. Horizontal axis, some 10 baseline covariates. And you can already see that the baseline covariates, most of them are binary or at most multinomial. algorithm. That's my current, that's the population for the current single-arm trial. And here's my external data. In the case of this application, the external data are actually historical trials run by the same team of clinicians, like in the same department in again. So it's really good historical data. Again, in the vertical axis are some 300 patients in the external data. In the horizontal axis are the baseline covariates. And the name of the game is now we want to massage the big plot, we want to massage the external data in such a way that the distributions of the baseline covariates are very comparable. Because then you can use the external data after the appropriate rating. You can use it for a synthetic control arm. That's exactly what I talked you through. Throughout the next few slides, I'll use red T to mark the current single-arm treatment-only study. I'll use blue C to mark the external data C because I should use them for a control arm. There are good reasons why they use single-arm treatment-only studies in this particular indication, glioblastoma, brain cancer. Using external data is of course a long-standing long-standing issue, and many people did intelligent things on it. Perhaps one of the most principled things to do in the context of patient inferences to use the external historical data to be the historical data file, and that is being done quite a bit. A bit closer to what we are going to do here, using the external data to create a synthetic control cohort. There are many approaches that are based on what is known as propensity scores. The idea of the propensity scores take the red data from the current trial, take the blue data from the external data, merge them. And now in the merged data, for each patient, we introduce a rating indicator set sub I. The set sub I is either blue or red to indicate whether the patient came originally from the blue or from the red data. So we get these propensity scores, the probability of the patient being red for a given covariance. And using these propensity scores, we can do all kinds of games. We use the external data as control data. Intelligent approaches, but we are trying to be much more stupid than these clever things. And we want to do something much simpler. We just want to relate the external data by way of setting up these aligned mixture models. So here's again the cartoon from the title slide. One important comment about setting it up like that is the two partitions have to be aligned, means they have to have the same clusters, otherwise we can't talk about the kind of weighting that I already introduced. But importantly, that partition is subject to uncertainty, so we just introduce the random partition. It's a random element, it's an unknown parameter, it's part of our MCMC. We're going to average over it across iterations. So we're going to set up a mixture model that needs a minimal notation. So here's my notation. I use I to index the patients. There's n patients. Xi are the baseline covariates. We are going, the aim is we want to adjust the two populations to make them comparable. But the only reason why we want to do that is because we want to compare them with respect to some response. Sadly, in the case of glioblastoma, the response is overall survival. Sadly, because it's short enough that you can observe it during time of follow-up. I use cap C sub K for the partitioning subsets for the clusters. I think that's all the notation that I need. Then here's just a stylized version of my mixture model. So we are setting up a mixture model for the Xi, just as a sum over the clusters. I use pi sub K. I use pi sub K for the weight for the K cluster. If the covariates were continuous, it could just be a simple mixture of normals like in this figure. One more little trick we use here that I like a lot. The components of the mixture. The components of the mixture we set up as independent kernels, independent across the covariates, so just vectors. Of course, setting up a mixture of independent kernels, you can still get arbitrary dependence, like a mixture of tomatoes and really beautiful cucumbers. But the important trick here is if the covariate is missing for some features, and in the case of our example, there was like some biomarker that we only figured out in recent years was important. So earlier studies would just not record this biomarker because they didn't know about it. If you're missing a covariant, well, then you simply skip that factor in the product. That's all. You don't impute or anything. Like no mice or whatever. I don't know. Mice is a popular algorithm to impute missing data. Totally ad hoc, but very popular. Yeah? And actually, in joint work with Fernando Quintana and Gary Page, we use exactly that kind of feature to set up regression with variable dimension covariant vectors. End of the version. Now we need not only one mixture, we need two mixtures for the two conditions. I was ready to look at it. My point is much better. The battery is stronger, but it's obviously not true. So I'm setting up the same mixture now, once in blue for the external data, once in red for the current treatment only study. Everything gets now blue and red super indices. Then I can create these two mixtures now. Now I have the green mixture for the external data and the red mixture for the current data. And everything is like indexed with that colored super index, except for the cluster centers. The cluster centers do not get a colored mark because they're not supposed to be shared to create aligned partitions. This was inspired by like there's many papers use like common atoms mixture models to set up aligned partitions for all kinds of purposes. One of the earlier ones was Francesco Denti, Michele and others using common atoms mixture models for microbiome at that time. In the context of that model, it's not easy to introduce the desired reweighting of the external patients. I think if you stare at these two mixtures, it's already immediately plausible that when you have inference in the blue, when you have a Monte Carlo sample under the blue model, the appropriate reweighting would exactly be the ratio of the weights, because that's the only thing that differs, right? And you can actually formally convince yourself that it's correct. You need to use the ratio of the weights to reweight the patients. You might get nervous about seeing a weight in the denominator that could be very small. Just using raw black realization in the MCMC, we replace the weight in the denominator by the conditional expectation, which is just the cluster size, the relative cluster size. So you put the relative cluster size in the denominator. And then one more thing. When we create the weight for patient I is in different clusters at different iterations of the MCMC, or saying in different words, the cluster membership is random, we do not know it. So we are averaging over the Monte Carlo sample the ratios of the weights of the clusters in which the I patient is placed in each of the iterations, and that turns out is exactly the correct weight that you need to approximate expectations for the red population using Monte Carlo samples for the blue population. There's a funny thing. So far, I only talked about the baseline covariance. We didn't talk about the outcome, right? Although, of course, the whole purpose of carrying out this study is to compare outcomes, to compare overall survival and dual determinant treatments. But once you have set up that random partition, it's very easy to add now a response model for the overall survival. What we simply do is for each cluster with a cluster-specific parameter to index a sampling model for the outcome. In our case, this is overall survival. This could be, for example, a simple exponential distribution. This could be the exponential mean. For the outcome model, of course, you want the parameters to be color-coded. They should not be shared. The outcome parameters, if they're shared, you would introduce zero treatment effect by design, right? So for each cluster, we get an treatment effect that could be expressed just as the difference of the red phi and the blue phi. And if we average that across the population, keeping in mind that our target population, our estimate, is the treatment effect in the red population, so we have to use the red rates, we get the desired treatment effect in the current population. Footnote, and I'll just tell you a one-line summary. The model actually also includes a notion we can estimate propensity scores, actually easily the way of propensity ratios. So if you want propensity scores, you can actually get inference on that. Model-based in this case, without assuming a particular model. Like, the typical thing in these approaches is they assume a logistic regression for the propensity score. And it always makes me uneasy because the propensity score is used for using a reciprocal for weighting, and the reciprocal, which means it's actually most important when the propensity score is very small, then you have the least confidence in it. But turns out you can do it. That's all I wanted to tell you about the first application. I have 3 more coming up, 9:45 or so. Yeah. So this is now the second application. That was the comparative immune profiling, where I had like clustering of immune cell gene expression for early onset and same thing for late onset. And we wanted to scale it to cluster arrangement to find out how the 2 populations differ, how the 2 disease conditions differ. This was joint work with Yunchan Duan, one of our outstanding PhD students at UT Austin. Moving now to Johns Hopkins. Are you here, Yunchan? She's sleeping still. Okay. He's probably working on the next paper. Juhai Wu, a graduate student at MD Anderson, and Benny Wang at MD Anderson Bioinformatics. I already told you the target is we want to compare early onset versus late onset CRC. It's a rising public health challenge, early onset CRC. There's more and more young people presenting with CRC. And it's not yet well understood how the 2 conditions are different. We are going to focus here on T cell subpopulations. So in the upcoming plot, what you see is gene expression features for T cells, for early onset patients and late onset patients. And we are back to the title slide. On the title slide, I showed you simulated data. This is not the actual data. This is gene expression features for T cells of early onset patients marked in red and late onset patients marked in blue. It's public domain data if you want to play around with it. Whenever I plot gene expression features, I always have a problem. First of all, the gene expression feature is high dimensional. I can only show you 2 dimensions on the screen. Second, it's customary to plot them with some nonlinear transformation. Whenever you see Disney or UMAP, there's a nonlinear transformation that enlarges like differences between the clusters. So don't get too excited about the beautiful clusters. Part of that is the nonlinear transformation of the plotting. But the main thing that we see here when we plot the data, we see that there is hope. There is hope for finding subpopulations that seem to be mainly red and other subpopulations that seem to be mainly blue. If this were just one soup, then it would be hopeless. Yeah? But this gives hope. This is just the data. We haven't done anything to it yet. Here's the inference. So after setting up our combinatorial mixture model, with appropriate biostructure coming up on the next slide, we get the following inference. We can cluster the data that I showed you on the previous slide. We can find inference for a partition of the gene expression features for early onset. And here is the same for late onset data. And if you stare long enough, this is the actual inference. If you stare, and importantly, these 2 partitions are set up in an aligned fashion, means you see the same yellow cluster here and there. And if you stare at that for long enough, we can probably convince ourselves that some subpopulations are specific to early and others are specific to late, and yet others might be shared. Is it also obvious, though, that to really make any meaningful statement, you probably, to make any quantitative statement, you need model-based inference, because otherwise your fantasy goes wild, yeah? Confounded with your fantasy is the fact that we have more late onset data than early onset data. So in your mind, you have to pre-process that before you compare, to take into account that there's simply more dots on the right side than on the left side. So we really want to set up model-based inference, and that's exactly what you and Sean did. In Igor's talk, he had a nice classification of probability models for dependent random measures. Can be constructed by additive decomposition, by hierarchical models, or by nested models. I thought it was a nice classification. In that classification, what we are using is we're using additive decomposition. In the display map here, you see the red mixing measure G1, the blue mixing measure G2, and you can immediately see G1 and G2 are the F stars. The F stars are just subsets of the atoms. The black F star, those are atoms that are shared by the two conditions. In plain English, the atoms in the black F star, those correspond to cell subtypes that are shared between the two conditions. They have nothing to do with early versus late onset. The atoms in the red F star, those are atoms that are more prevalent in the red early onset patients. But again, it would be biologically implausible to assume that they are absent in the other population. You just assume they are less common. Same story with the blue atoms in the blue F star. To achieve the desired interpretation of the red atoms being more common in the red data, we simply set up an estimated Dirichlet distribution trial for the red rates to achieve the interpretation. That's actually it. In case you wonder about the title, the name of the model, 888 model, they didn't let us use the name in the end anyway, but we liked it. The black one was had 8 atoms, 8 red atoms, 8 blue atoms. We don't want infinitely many atoms because you cannot possibly interpret infinitely many cell subpopulations. Yeah, there's like on one hand there's like a never-ending classification, refinement of different cell types, like there's white cells, the white blood cells, there's T cells, there's blah 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 blah. It goes actually quite a bit. But with a finite amount of data, you cannot hope to interpret more than a certain number of subtypes. There was something I wanted to tell you. Oh, the 8. So we used 8 black ones, 8 red ones, 8 blue ones, because 888, the Chinese here sounds like money, money, money. But they didn't let us keep the name, unfortunately. And there's a wonderful Chinese restaurant in Houston, the name 888.
Why not 6?
Sorry?
Why not 6?
666. Diversity inclusion, actually, we want everyone to be comfortable. So this is the same inference again. I already showed you that slide. Just adding here on the left side the same random partition in the merged population. In principle, you could do the following thing. Instead of setting up a complicated model with 2 dependent random partitions, you could just merge all the data into one partition and then try to tease out which of the clusters is specific to one or the other. The problem is, when you do that, you would want to make sure that each cluster has some red and some blue cells, and you want to make sure that you allow for the relative proportions to be, you want to multiple shrinkage. You want to see like some subtypes that are predominantly blue, some that are predominantly red, and by the time that you include all those conditions, you're exactly down to our model. It's kind of easier to start with 2 random partitions instead of taking one random partition and imposing all the constraints. This is again the same thing, just taking the plots apart now, splitting them into the black atoms. So the black atoms, the blue and whatever that color is, those are cell subpopulations that have nothing to do with early versus late onset. The red ones are characteristic to early onset. The blue ones are characteristic to late onset. So this could give rise now to hypothesis of which the subpopulations are those, what might be the mechanisms that are different for early onset CRC, and that might facilitate scientific learning. And getting into the third example, this is again joint work with Yunchan Duan from UT, will be in a few weeks at Johns Hopkins. Shuai Guo, Hao Yan. Shuai is a graduate student, a PhD student at MD Anderson. Hao Yan is a postdoc, and Wen Yi Wang is in MD Anderson Bioinformatics. So here's what we're doing in this problem. After some pre-processing, so we use spatial transcriptomics data. I think we already had some talks using ST data. But after some pre-processing, the data that we see is we see cell level data after pre-processing, and those who know, they know what's behind that sentence. After some pre-processing, we have cell level data where for each cell we get gene expression features. So YGI is the gene expression. G in this application will index the two different kinds of cells. We'll have tumor cells and immune cells. And remember again from the title slide, the inference aim is we want to make inference about, we want to allow English sentences like tumor cell type A recruits immune cell type B. We want to formalize such sentences. So J equal 1 is blue tumor, J equal 2 is red immune cells. And so for cell YGI, for cell GI, YGI is the gene expression features. We find it useful to introduce an additional superscript to separate tumor gene expression features and immune cell gene expression features. For the simple reason, there's no reason why one should have anything in common with the other. Yeah? For a tumor cell, we would only have here YGI for J equal 1. For an immune cell, we would only see YGI for J equal 2. And importantly, additionally, we have the yellow subvector, which is just the spatial coordinates, literally the spatial coordinates on the tissue slide. So we have the yellow spatial coordinates and the gene expression features. And again, we want to find homogeneous cell subpopulations with the fiction that those correspond to meaningful cell subtypes. And the additional fiction, we assume that these cell subtypes are exactly the classes that you see under random partitions. It's obviously not exactly true. Actually, one of the things we are trying to do now, we want to use cell type annotations, the formal data, and make use of that. The inference target is we want to talk about some red J equal 2 clusters to be spatially aligned with blue J equal 1 clusters. That's where this is headed. Here's the data. I split the data into two parts, the yellow part and the gene expression features. So on the left side, each dot is a cell, including tumor cells and immune cells. I think the red ones in this case, sorry to switch the colors on you, the red ones are the tumor cells, and the non-red, those are immune cells and more. And when you stare at that figure, again, if you stare for long enough, you can probably start some narrative of some types being aligned with some of the tumor cell types, but it takes a lot of fantasy, yeah? So we need volume-based inference to make that statement a little bit more formal. On the right side, you see the gene expression features. Again, with the caveat, this is plotting like the first 2 dimensions of a nonlinear transformation that accentuates the differences between the clusters. But there are certainly well-defined clusters in the data. This is just the data at the moment. There are certainly well-defined clusters in the data, and there's hope to make inference. Again, we are proceeding exactly the same way as before. We are setting up 2 common atoms mixture models. The only thing that is different now, in our prior for the 2 mixing measures, we set up the prior for the 2 mixing measures in such a way that the 2 yellow coordinates, the spatial coordinates of the immune cell clusters, they should be allowed to be spatially correlated with the tumor cell clusters. Allowed means there might very well be immune cell types that are not co-located with tumor cell types, but they could be. And that's exactly what you see now here. The first two lines are again just back to slide number 2 or 3 when I talk about the notation for the mixture model. The first two slides are just setting up the mixture model for the two kinds of cells, for tumor and immune cells. And the next two lines are the prior on the mixing measures. We have a prior on the mixing measure G1 for the tumor cells. And we have a prior on the mixing measure G2 for the immune cells. And that's where the magic happens. We are setting up a big manure process with base measure G2 star. And in the G2 star, that's where the action is. And the G2 star, sorry, the G2 star, again, the G2 star has like the spatial part to it and the gene expression feature part. In the spatial part, we do the following thing. In the spatial part, we are setting up a mixture. We are setting up a mixture where the spatial cluster locations can either be generated independently from a G2 tilde, or, and that's where the rubber hits the road, or whatever is your favorite metaphor, or the spatial cluster locations can be just centered around the tumor cluster locations. They need not be exactly on top of it, so they don't have to be literally aligned. They should just be around it. Yeah? Although they could even be literally on top of it, because immune cells are much smaller than the tumor cells. So it could almost be like you can sprinkle the tumor cells. You can sprinkle the immune cells on top of the tumor cells. So this last line is actually, that's the main thing that will facilitate our inference. So it's again that common theme with the previous two applications. We are setting up a vanilla probability model for inference and dependent random partitions. The only special feature that I really wanted to talk you through here is that the nature of the application, the desired inference, gives rise to a very special prior structure that we want to introduce. And those are like variations in prior structure that you would never dream up if it were not motivated by the application, yeah? Or if you were to dream it up, nobody would take you serious. This is the inference, showing you exactly the kind of inference that we wanted to produce. I just pulled it apart into 4 separate figures to make it easier to see. Oh, the color underneath, this is just literally the tissue slide. This is just the data. The dots, the blue dots, here that's one tumor cell cluster with the blue ellipse showing the tumor cell cluster, and the red dots, that is an immune cell cluster. That's an immune cell cluster that obviously generated its cluster location using the second yellow part in the G2 star. Like if you remember the G2 star, obviously the cluster center for that particular red cluster was generated from the yellow part because it is aligned with the tumor cells. And here's for 3 more, here's for another tumor cell type. You see the aligned immune cell types. Importantly, by the way, also need not be a one-to-one thing, like one tumor cell type can recruit multiple immune cell types. Yet another one, I should have included some immune cell types that are not aligned with blue ones. Yeah? There are some immune cell types that are not aligned with blue ones. I didn't, unfortunately. How much? 5 minutes. So you can still quickly advertise the third example. This is joint work with yet another super smart new PhD student, Entecher, sitting right here. Entecher, who is not sleeping in. This is joint work with Entecher alum and Paul Rathos, one of our colleagues at UT Austin. Quite a different application, but in the end it will look similar. It's again going to create random partitions with common atoms. When I planned it, I was hoping that I can give the talk before Entecher can give the poster. It's the other way around now. So it be, I edited a poster on Monday, some of you might have seen it. Here's the story, just simple vanilla GLM, generalized linear model. So here's a GLM, I use F0 for the baseline density. And then the B is just the log normalization constant. And this is the exponential tilting that you use in the GLM to achieve an expectation of the outcome for conditional covariance X to be related to the linear predictor X prime beta by the affiliate function, like vanilla standard GLM setup. It becomes non-parametric, sorry, it becomes semi-parametric. If instead of using a parametric model for the baseline distribution, like instead of using, I don't know, a Poisson distribution for F0, if you're going non-parametric on the F0, then it becomes semi-parametric, and that's something that Paul Rogers has done a lot in previous work, but just using MLE for the baseline distribution. They call it the SVGLM, semi-parametric GLM. The thing is obviously screening for BNP implementation instead of using the MLE. The MLE, as might be plausible to many of you if you have done similar things, the MLE is a distribution that's only supported at observed data points. Kind of, yeah. I'll make it more formal in a second. So this is obviously screening for a BNP version. What we simply do is we put the Dirichlet process prior there. No, that's getting easier than that. Even a little bit easier, since we anyway have the normalization constant in there, we don't even need a Dirichlet process prior. We actually use an unnormalized gamma process. That's actually all that's to be said about it. The rest are really details, and I just want to talk you maybe through one detail or just summarize them. Turns out when you look just at the implication for the marginal distribution of, let's denote with F sub x, the implied model for a data point with covariant X. The implied model for a data, the implied sampling model with covariant X is simply the baseline distribution with the exponential tilting using theta tilde X, where the theta tilde is implicitly determined by the GLM logic. It turns out if you put the completely random measure prior on the F tilde, then the exponentially tilted thing is again a completely random measure. When we normalize it, it's a normalized completely random measure, but now with homogeneous level intensity. Second item, like just 3 observations about it and then we wrap up. Second observation, I think of that as a variation of an EDP. And I want to say it more formally in the next slide. I'll have to say kind of EDP because it's not exactly an EDP. And third observation, many of you might know the algorithm in the old paper by James, Lehoy, and Prinster, 2009 in the Media Journal. The same algorithm goes through the exponential tilting, doesn't really change much, yeah. So just quick comment on the second item about the DDP. Remember again, we are putting a Dirichlet process prior on the baseline distribution F0. And if you just hit that F0 now with the exponential tilting, you will take the right. All of it does is it takes each of the weights in the discrete random measure of the Dirichlet process, and it multiplies the original weight with the e to the theta I. At that moment, where the theta is really a function of the x, at that moment we get then covariant dependent, weights. But of course, after the exponential tilting, it's not the Dirichlet process anymore. That's why I can only call it like kind of a Dirichlet process. And if you want to have more details, catch there. Then that's really all I wanted to tell you. I talked you through model-based inference for aligned random partitions. I tried to convince you that in many applications, aligned random partitions become a useful tool to work with. Typically, you have to fudge around in the prior to create the kind of structure in anticipation of the inference that you want to report. Like if you want to report cell types that are specific to one or the other kind of one or the other condition, then you better introduce an appropriate structure in the client. And same thing for the spatial transcriptomics data. If you want to report about spatial alignment of different subtypes, then you better introduce the same structure in the client. And that's exactly what we did. Obviously, many limitations remain. One massive limitation is gene expression features to start with. They are massively high dimensional, and maybe the point to always refer to is not as gene expression or gene expression feature, because in pre-processing we have to do dimension reduction. Potentially, you could make the dimension reduction, of course, part of it. I just gave it here. Another monster, of course, is when I showed you the pretty pictures of the estimated partitions. I had to do something to summarize the possibilities between the random partition. For example, using Salto, for example, using Caravanian weights, or for example, some of you might have seen the poster, or some of you might have been in high school who had another very smart and clever way of summarizing random partition Kai's right there. If you're interested in variations of summarizing random partitions, ask Kai, very clever idea, yeah? Very clever trick. And we pay you to read it if you want to, yeah? Thank you.
Thank you, Rita. We have time for a few questions.
Thank you for a wonderful talk, and I was very interested in the very first application where you contrasted the two populations in the treatment arm and then the control population. And I appreciate not using the causal law in that thing, but I wonder if you, in some university, would think of those effect estimates as solution average effects or average effects in a so all solutions.
You want to expect the only average treatment effect. Average treatment effect in each population. We reported average treatment effect in the entire population, just the population of the target system and file. In the course of the inference, what we really end up doing, we end up imputing the potential outcome from the patients if they have to treat them in the group controller. So in that sense, we would swing and cause the interpretation there, and we have to make all these assumptions.
Perfect. Other questions? Yeah, thanks, Peter, for the wonderful talk. So for the first part, you used some kind of a basically piecewise constant function for the almost piecewise constant, not exactly because your cluster overlap. For the ratio of the cluster sizes, and use that to correct for your sampling. So one assumption that goes into that is that the heterogeneous treatment effect cluster aligns with the covariant cluster that you're using, because that's how you calculate the average treatment effect. In your typical application, is that kind of a do you have thoughts on how you may use that to do some more flexible heterogeneous treatment effect estimation?
Good comment, kind of goes in similar direction to Donatello's comment. Quick answer. In the cartoon, it was shown. I showed like specific clusters and strict cluster overlays. As you already mentioned, there of course, even in reality, even for a current with imputed partition, the cluster boundaries are cheap because we typically use as a good about kernel. On top of that, we average over the random partition. So actually, in the end, what you get a propensity to get those ratios and weights. Like for the nature of the ratio, sorry. So even for a currently imputed partition, the ratio of weights as you slide the covariance, when you're close to one of the cluster centers, you're getting the ratio of the weights for that cluster center. As you're moving to the next cluster center, there's a smooth transition to the propensity score, to the propensity ratio that's applied to the next cluster. So it's actually very continuous. And then on top of it, we marginalize the effect of the partition. So at the end of the day, there's a very smooth transition. There's no motion of sharp change points. That was really only the control stuff.
Perfect, so let's thank again, and Peter.